Hello, Physics 2. All right, so welcome to Wednesday's lecture. So we've been talking about Faraday's law and looking at the relationship of the time-varying magnetic field as it relates to driving an electric field, and also how you can use this to now calculate the EMF associated with this new non-Coulomb electric field. All right, so I have a lot of examples planned for this chapter, so we're going to start out this with yet another example using Faraday's law. So we have a high resistance wire. So resistance is equal to 75 ohms, and length is 4 meters, is bent into a square that encloses a solenoid. With magnetic flux changing from 7.5 Tesla meters squared to 4.5 Tesla meters squared in 0.2 seconds. So essentially we have, here's our solenoid, and here is the wire that has been bent around it, which now, because of that non-Coulomb electric field, can have a current being driven through it. So what we want to look for, based on these parameters, is the EMF, the non-Coulomb electric field, and the current. Okay, so let's start off with part A, looking at the EMF. So the EMF is equal to minus the rate of change of the magnetic flux. In this particular problem, we've been given the magnetic flux. So we know it's going from 7.5 Tesla meters squared to 4.5 Tesla meters squared. And this is occurring over a time period of 0.2 seconds. So this is equal to minus 4.5 minus 7.5 Tesla meters squared over 0.2 seconds. And so the EMF is equal to 15 volts. All right, so part B, we want to look for that curly electric field. So EMF is equal to the path integral ENC dot DL. And so we have EMF is equal to ENC times L. So we've been given the length. So just walk around. There we go. Okay, so we have ENC is equal to EMF divided by L. This is equal to 15 volts divided by 4 meters. And so ENC is equal to 3.75 volts per meter. So in this particular problem, if you remember, we were given the total length of the wire. We could have bent it into whatever shape we wanted. So we could have, say, bent it into a heart shape, and it wouldn't have changed a thing. It's the total length that is important. The shape is irrelevant. Okay, so part C, we wanted to know the current. So we have EMF is equal to the current times the resistance. So the current is equal to EMF over R. We've already calculated the EMF. It's equal to 15 volts. The resistance was given to us, 75 ohms. And so this is equal to 0.2 amps is equal to the current. So that is how you play these games. All right, so moving on. Typically, we will write EMF is equal to the path integral ENC dot DL to represent a curly non-Coulomb electric field inducing EMF. Okay, so we're going to look at this a little bit more deeply and keep building on these concepts. So, EMF can actually be calculated in terms of the total electric field E net. And this includes the Coulomb electric field, which would come from a stationary point charge. So E net is equal to the Coulomb electric field plus the non-Coulomb electric field. So this one's curly, and this one is the typical vector field that we're used to looking at. So from here you get the more correct expression, or the more complete expression. That's a better way of saying it. The EMF is actually equal to the path integral of E net dot DL. Now you might be thinking, wait a second. We talked about Coulomb electric fields and path integrals, and they're zero, because we need to have a curly field to get a non-zero path integral. But this is still true, because EMF is equal to the path integral of E net dot DL, which is equal to the path integral of EC plus ENC DL, which is equal to, we can split this integral apart into EC DL plus E non-Coulomb DL. Okay, so if you recall, this is equal to 0. And this is true since EC dot DL is equal to 0 for any Coulomb field. And we talked about that in the last chapter. Okay, so now that we have a more updated expression for EMF in terms of electric field, let's look at the EMF for a coil with many turns. So this is typically what we're going to be dealing with, is we're going to be dealing with objects that have many turns of wire on them. Okay, so this is actually practical and has real life applications. So we're going to look at the EMF for N loops. So this would be a coil where loops are very close together. And the non-Coulomb electric field is about the same for each loop. And the EMF is the integral, which is just another way of saying the sum from one end of the loops to the other. Okay, so EMF is equal, as we sum under the number of n terms, ENC dot DL. So then you would just multiply this by a factor of the number of turns n, and you'd have ENC of one turn. And so this is just EMF is equal to the number of loops times the EMF of one turn. So when you've got a coil of wire where they're all closely bound together, then you would just scale the EMF as a function of the number of turns. So essentially you've got, your solenoid that you are varying the current and thus varying the magnetic field, and then you might have all of these turns around it. Okay, so this brings us to Faraday's law for a coil. So EMF is equal to minus N times the magnetic flux over dt. So essentially, we now have an expression that will account for the number of coils, so you can scale it accordingly. Okay, so let's keep building. Faraday's law and a moving coil or magnets. So, and I do have a couple more examples in this particular section, some of which have moving magnets and some of which are the typical variation we've been seeing thus far in terms of applications of Faraday's law. Okay, so we know we can get dB dt by varying current in a coil. You can also have a time-varying magnetic field where, let's say you had a coil of wire with a magnetic field that is moving towards this. So, this is the coil of wire with the magnetic field. This wire is moving towards it. So if this wire is moving towards it, this wire is experiencing a non-zero time varying magnetic field. So if you've got the wire coming towards this magnetic field, so remember, magnetic fields, like electric fields, will vary as a function of distance. So this is constantly changing distance with this coil of wire, which has a magnetic field. So that's one way that you could drive a current, is that you could just simply change the magnetic field by changing the distance. Whew. You could do the same thing with a magnet. So if you take a bar magnet and you move it towards a coil of wire, you'll get a magnetic field. And then once again, because this magnet is moving towards it, it's going to have a time varying magnetic field. And so once again, you can drive a current in this wire just by moving a magnet in and out of a coil. This is something that you can demo in lab And then, of course, you can also have a situation where if you take a magnet, and this is often what's done to generate currents, and you spin it. So let's say you had a coil of wire here. Once again, this would generate a time-varying magnetic field. So this coil here would be experiencing a constantly changing magnetic field, which then would drive a current through it. So this EMF by dB dt non-zero can be driven in a lot of different ways. Basically, you just need to have a magnetic field that is changing in some way with respect to time. So logically, all of these make sense. So all three of the previous demos, drawings, have a changing magnetic flux. So what would be true for all of them is the EMF is equal to minus N times the time varying magnetic flux, which is equal to minus N d dt B1 and hat delta A2. Okay, so we're going to start a series of examples. Starting off first by looking at EMF from some moving fields and then going into some more examples of Faraday's law. So the best way to learn how to do these types of problems is by just doing a lot of them. So, example. We have two coils of wire are near each other, 45 centimeters apart. Coil 1 has a radius of 10 centimeters and 5,000 turns. And the current in coil 1 can vary. Coil 2 has 2,000 turns and a radius of 6 centimeters. It is rotated 62 degrees from coil 1. Okay, so we've got coil 1, which has 5,000 turns. Radius of 10 centimeters. We have coil 2, which is rotated. (62 degrees) and equals 2,000 and 6 centimeters. These are 45 centimeters apart. Okay, so we have more information. I1 varies from 2 to 7 amps in 6 milliseconds. And we want to look at the induced EMF in coil 2. All right, so we're going to go through this problem step by step. So, we need to find I1. Then we can find B1 at 2. So if we can find the current from coil 1, we can start to go after the magnetic field at the location of coil 2. So we know that di1 dt is non-zero, and we know what it is. So using this, we can find the change of magnetic flux with respect to time in coil 2. The change in magnetic flux with respect to time is going to give us EMF. So, as you're setting up these problems, thinking through what you know and thinking what you know and how you can use what you know to find what you need to know can be a useful strategy. All right, so let's look at the assumptions we're going to have to make. Coils are far enough apart that the magnetic field is relatively uniform. And the length of the coils is small compared to the distance between them. All right, so B from coil 1 at coil 2. So B1 is approximately N1 mu naught over 4 pi 2I pi R1 squared over Z cubed. So just an expression that we're used to. Thinking about the magnetic field from coils of wire. So the magnetic flux generated for one loop of coil 2 is approximately B1 pi R2 squared times cosine of theta. Okay, so we can put these two equations together. So this is the magnetic field that we can insert into there. So doing that, we get that magnetic flux is equal to N1 mu naught over 4 pi 2 I1 pi R1 squared over Z cubed times pi R2 squared over, times cosine theta. Okay, so I1 is the only quantity that is changing. So everything else in this particular equation is going to be constant over the time that we're looking at. So we can go after the EMF of one coil. So EMF is the time varying magnetic flux, N1 mu naught over 4 pi, 2 pi r1 squared, pi r2 squared over z cubed. This continues down. Cosine theta di dt. So this is all supposed to be on one line. Let me just write this out. And notice that what we've done is we've isolated the term that is the actual time varying term. Okay, so the total EMF for all of coil 2, EMF is equal to N2 times the time varying magnetic flux is approximately N1, N2, mu naught 4 pi 2 times pi r1 squared, pi r2 squared over z cubed cosine theta di dt. And we can just plug and chug now. So this is equal to 5,000 turns for N1 times 2,000 turns for N2. 1 times 10 to the minus 7 Tesla meters per amp times 2 times pi squared times 0.1 squared times 0.06 squared cosine of 62 degrees times 7 minus 2 amps. The time or the current, the amount that the current has changed, divided by 0.45 cubed. This would be the distance between the two coils, times 6 times 10 to the minus 3 seconds. This is the 6 milliseconds that it took for the current to change from 7 to 2 amps. And from this we get EMF is equal to 3.05 volts. There you go. All right, so that ends part 1 of Wednesday's lecture. We will pick up next time with a few more examples for part 2.